Hi all, and welcome to the Medical AI Lab talk series. I'm delighted that today we have Chenwei Wu presenting a paper on domain generalization, which is Ensemble of Averages, improving model selection and boosting performance. Chenwei, take it away.
Hi all, my name is Chenwei at Harvard Medical AI Lab. Today I'm gonna give you the presentation of this paper, Ensemble of Averages by Salesforce AI Research. So I'm gonna go through the motivation, background, and previous work prior to this paper. And then I'm gonna briefly explain how the authors approach Ensemble of Averages by a two-step approach. And then I will share the results and talk about advantages and also limitations of this approach. So first, we have to understand what is domain generalization. So to achieve domain generalization, it means we're gonna learn predictors that generalize well on test distributions that are generally shifted away from train and validation distributions. And it's quite hard in a real life scenario because for a fixed data set and model architecture, there are so many distinct ways that a training model can achieve high validation performance, but not good test performance. Because under standard practice, models that encode distinct solutions are often mistreated as equivalent just because they're held out predictive performance like the validation accuracy is equivalent. So these distinct solutions between models, they do become very clear when they are measured on criterion beyond standard performance like accuracy. So when they're measured on fairness or their robustness to irrelevant input perturbations, the distinctions will show very starkly. So for example, like among models that perform equally well on validations, some may exhibit greater performance disparities across ratio groups or rely on heavily irrelevant information. So yesterday I was doing a machine learning homework that classifies pneumothorax by chest x-rays. And the model initially had an AUROC of 85%. But later, after further analysis, it turned out that the models is just classifying pneumothorax based on chest tubes or other medical implants like a pigtail catheter. So these differences can translate into huger gaps in real life applications. And we definitely don't want that. And these could originate from like small differences like random initialization seeds, data ordering, hardware differences, and so on. So here I will give you an example of ImageNet versus ImageNet-C. So we all know that there are already plenty of models that perform super well on ImageNet. And ImageNet-C is basically adding a lot of random perturbation to the original ImageNet dataset. And so we can see the two graphs on the left. They correlate to like two identical models, but with different random initializations. So the lines represent the performance of each model in the ensemble classification task using uncorrupted dataset, which is on the leftmost, and also corrupted dataset. And we can see there's huge discrepancies between these two randomly initialized models. So from this, we could see the performance of an arbitrarily selected model to show how performance on one test may not be a good indication of the performance on others. So people have done work to illustrate this model selection problem. So one of the previous work that actually illuminated the creation of this ensemble of averages paper is domain bed. So it basically develops a PyTorch testbed for domain generalization streamline, consisting of three parts. First is dataset. Second is like some baseline algorithms. For example, ERM, which is used a lot for domain generalization. And also most importantly, model selection. So the paper put a lot of stress on model selection, and it actually says domain generalization algorithms without the model selection strategy should be regarded as incomplete. And so here's a data set of the domain bed. We can see that for each data set here, in this image illustration, like one single class is picked, and here are like different domains of the same class. For example, like rotating them with each other, and like in the bottom domain net, we have different genres of drawing of the same image. And for the model selection strategy, yeah, used a lot. And so, for example, yeah, used train domain validation set. So this one is quite simple. Is basically we first subset the training set for each domain of the image into train and validation. Then we pull from the all the domains and generate like a final big validation set. Another model selection method is called leave one domain cross validation. And so it's very similar to regular cross validation that we do, except for the left out is a domain. So it's like a, so like, for example, we have like 10 domains here. For each round of the cross validation, we leave one out and compute training on the rest 9. And in the end, we evaluate the model based on the performance on the left out domain. So already having domain bad, why are we needing this paper, ensemble of averages? So so the domain bad does address a lot of importance in model selection, but the authors here questions like how reliable are these model selections are. So, because despite the importance of the model selection, there hasn't been much investigation into their reliability. Because as we look at this graph, the out of domain performance, which we can see in the bottom part, the test domain, which is out of domain, versus the validation in domain accuracy. The in domain accuracy, although it is very stable along the optimization trajectory, but the out of domain, it is not. We can see like the accuracy and loss are oscillating very hard without this EOA approach. And the authors, after applying EOA, they were able to stabilize this and make the model selections based on these performance more reliable. And this is also gonna increase, the EOA approach is gonna increase a lot of the rank correlation. As we can see here, the in-domain validation accuracy doesn't have really much to do with the test domain accuracy, while after averaging, it does. So this is very simple but effective methods, and you basically take the idea of moving average, and you can achieve the whole approach in like a page of code. So it's very efficient. So to understand how EOA is achieved, we're gonna divide into 2 parts. So first is how moving average works on like a single model. And the second step is how moving average works for ensembles. So how do we achieve EOA? So to understand the moving average for a single model, we're gonna first give some definitions. So first, the definition is like a online model. So for a given supervised model, like for example, we're estimating function f and the theta related to function f, and the ground truth, let's say, is y equals to 2x plus 1. So maybe at step 0, we randomly initialize it to 1x plus 0.1. And after like a total of 1,000 steps optimization at step 500, we have 1.5x plus 0.8. And at the end, we have like 2x plus 0.99. So like each step is considered like a online model or an average model. And in contrast to this online model, we have our moving average model. So when we're training these online models by steps, we maintain a moving average of the online model's parameters and just apply a simple moving average to it. So this concept is known as iterative averaging. So there are generally 2 types of iterative averaging. So there's one called geometric averaging. If you're familiar with the discount factor in economics, basically the income that you receive in the future should be discounted when compared to income received today. So it's similar for geometric averaging. So we basically apply a shrinkage factor to later weights as opposed to the previous weights. And there's also an idea of tail averaging. So instead of calculating the moving average starting from initialization, t is 0, we actually set manually like a t0 ourselves. For example, like 50 means we start calculating the average at steps 50, and we keep calculating the moving average till the end of the training. So the author used tail averaging here. My guess is because geometric averaging is gonna reduce variance, so it's gonna maybe like work better for small or fully conditioned data. And here, like the data is kind of big, so the tail averaging, according to a paper in 2017, is gonna reduce bias. So probably that's why tail averaging is used here. We can look at the formula here. It's very simple. So if t is before the not randomly, like manually set t0, um, the theta t hat, which is the moving average parameter, is basically the online model parameter. But otherwise, it's just a simple moving average of the previous theta t and the theta t hat. So during cross-validation, we're using the moving average theta hat instead of the online model. And this will help us include the rank correlation between in-domain validation accuracy and out-of-domain test accuracy. And we'll elaborate on this later. So the authors also did some experiments on the hyperparameters. So first, they're trying out different T0s. So they're trying like, let's say, how do we see the performance change when we average from T0 equals to 0 and to 8,000. And so they actually found that choosing like a T0 other than 0 is going to help, because if we still use T0 equals to 0 as initialization state in model averaging, this is going to cause a slight dip in performance because the initial loss is like really high. But after like adding the number of iterations for T0, like the results don't change much. So they arbitrarily just set 100 as starting point for the remaining experiments. And another thing they experimented and controlled on is the averaging frequency. Because for simple moving average, we're like calculating SMA for every iteration. And here instead, the authors are considering like trying out different frequencies, for example, like 10, hundreds, and 1,000. But they concluded there's no major impact. And so in the end, for the later experiments, they're just using 300 as the averaging frequency. So here's a qualitative analysis of how the moving average methods of weights is affecting the test domain accuracy. So the Terra Incognita is one of the datasets inside the domain bed framework we just discussed. And here is illustrated as an example. So on the left side, we can see the testing accuracy is oscillating and very stable. Compared to after applying moving average, it's like quite stable and smooth. So the rank correlation is another good way to quantitatively measure like how well our moving average is doing, because like to actually select model based on our validation accuracy, we do want like validation accuracy to have some really good correlation and positive correlation with our test out of domain accuracy, right? So using rank correlation is gonna measure like how well the average is doing, and the closer to 1 is better. And here we can see a lot of them are doing quite well. And however, I have to point out this is the rank correlation within the same run. So this is for like a single run model. And the improvement in rank correlation doesn't apply for a single model, but with different runs. But this problem is going to be discussed and solved by Ensemble of Averages later, and we'll also discuss that. So, okay, so let's move to Ensemble of Averages. So instead of applying moving averages to a single model, we can also apply it to ensemble models. Because in the bottom, the same dataset, Terra Incognita, you can see even the ensemble models are having this problem of lower rank correlation and unstable test accuracy along the optimization path. So what Ensemble of Averages do is very, very straightforward and simple. It basically creates an ensemble of multiple independently trained models with different hyperparameters and Cs, for example, and where each of these models are moving average models from their corresponding runs. So the difference of EOA versus ensemble models is that ensemble models have these online models where EOA have moving average models. We can look at the formula of this. And so here, E is the total number of models in the ensemble. The theta I hat, I think it denotes the parameters of the i's moving average model. And the superscript K is like class. Yeah, and so it's very simple. And so the settings and the experiments they ran was they trained different models, total number 6 independently for 5,000 iterations, using different C's, hyperparameters, and the training validation splits. And these are all identical to domain bed to like keep a benchmark. So we can see the method of applying moving average also performs so very well on ensembles. And looking at the rank correlation for all of these data sets, you can see there's a great improvement from the without averaging. So they also did an evaluation of ensemble moving average versus the previous state of arts using actually 2 pre-trained models. So the first pre-trained model they used is a ResNet 50 pre-trained on ImageNet. And the second one is a ResNet Next 50 32 by 4D. And so this is a pre-trained model using semi-weekly supervised objective on the dataset IG1B. So this is a huge dataset containing like 1 billion weekly labeled image and ImageNet labeled data, of course. So they both have the same amount of parameters, these 2 pre-trained models. The author stated that the choice of these 2 different models is that like recent trains in deep learning shows that models like pre-trained on larger data sets is generally gonna perform better on downstream tasks. And yeah, as we all know, this is true. So they're just testing on these 2 and seeing if the ensemble of moving average is gonna improve the performance of both models. And so here we can see it actually does, and it outperforms not only the single models and ensemble models, and also the previous state of art SWOT. So here for the VLCS dataset, the SWOT is actually performing like slightly better than ensemble of averages, but the authors argue that SWOT use a lot of hyperparameter optimization, and while in ensemble of averages, they did not use any hyperparameters tuning and just stuck with the original settings we talked about in earlier slides. And so it's still kind of better than SWOT even on this data set. So in conclusion, what this simple but effective approach gives us is that ensemble of averaging models, they outperform ensemble of unaveraged models. And same goes for single models. And this model averaging approach, like they significantly improves the rank correlation between in-domain validation accuracy and out-domain test accuracy. So what this means is if we train applying this ensemble of average models, it's gonna make our model selection more robust and more reliable when it comes to domain generalization problems. So however, there are still some limitations. So recall when we were talking about the single model moving average comparison with single model without like a moving average, we're saying that rank correlation table was only for within a run stability, but not across runs. So they actually reported that the gap in performance between different runs still exists, despite it's like kind of smaller for average models. So there's still diversity among different runs, and this is probably like why like the ensemble of averages performs like much better than only applying like moving average to individual models. Yeah, and that's it. So I think what we learned from this paper is that something as simple as like a moving average can help us understand and improve our model selection much better. Thank you. That's all.
That was a fantastic presentation. Thanks, Chenwei.